In this example, we're asked to use the logic definitions of the set operations to prove this half of DeMorgan's law for sets. This one says that the complement of A union B is equal to the intersection of A complement with B complement. And so we proved we showed in the last video how to construct, not this one actually, the other half of DeMorgan's law using a Venn diagram, and to justify that DeMorgan's law was true using a Venn diagram. Now we're going to do this using the logical definitions of these things. So we haven't actually, this says to prove, right? We haven't actually talked about what is going to be expected of us in terms of mathematical proofs yet in this course. And so for that reason, we're not going to write a formal, what we'll eventually call a formal mathematical proof to prove this, but we will write down the logic definitions of these sets. Well, you have to start with one of them, and then use only logic to manipulate these two things, or whichever one we start with, to get the other one. So let me just get into it then. So let's start with the left-hand side. You could start with either side, it doesn't matter, but you start with only one side, and then we're going to produce the other side, okay? So the logic definition of the left-hand side, we would just say, let X be a member of A union B complement, okay? And what I'm going to do now is just string together a bunch of consequences of this definition, okay? So remember, the complement is always, it's always relative to the universal set. Now, when we're not given a universal set, we don't have to write it down. We don't have to say anything about what the universal set is. We just assume that it exists, right? So there's always a universal set somewhere. And the complement means then what? That if X is in the complement of A union B, then X is in the universal set, but X is not in A union B itself, right? So it's not in A union B. All right, from this point, I'm just going to start drawing arrows that kind of represent implications. Like I said, this is not going to be a formal mathematical proof by the standards that we'll have later, but for now, it's going to be good enough. So if X is not in A union B, if it's not in the union, remember the union is the collection of all elements that are either in A or in B or in both, right? This is the disjunction of our logic, basically our logic, right? So this then means, right, then, I said I was going to draw arrows, so I'll stick with it. This then implies, right, that X is not in A and X is not in B. Okay, so it can't be in either one. If it's not in the union, then it can't be in either one of them individually, right? If it was in either one of these individually, then it would be in the union itself here. And then we can kind of unwrap exactly what we did before, right? So this then further implies, because it's not an element of A, this must mean that X is an element of A complement, and similarly, X is an element of B complement, right? And if X is in both the complement of A and it's in the complement of B, then therefore X must be in the intersection, right? So X is in the intersection of A complement with B complement. All right? And if you wish, as you go, and by the way, that's what we wanted to prove, right? So, whoops, I didn't really write it correctly. I think I said it okay, but I didn't write it correctly. So all I had to write here was that X is in the intersection, right? The intersection of A complement with B complement. So this "and" here is the intersection of set theory. And so notice that's exactly what we wanted to prove. So that's it. That's the end of our proof. At the end of our proofs, we usually draw this little, you need to draw something to indicate that the proof has ended, right? And so in math, a lot of math books and mathematicians draw this little box. And this box has a name, and it's kind of a morbid name. This is called a tombstone because the idea is that once you see the tombstone, that means that the proof has been laid to rest. Now, I don't make this stuff up, guys, okay? That's not something I'm making up, but that's truly what this is called in math circles. Now, that's kind of got bad connotations, so I like to always add a little smiley face next to the end of my proof symbol. So now we've finished the proof, we're smiling, we're happy. And we believe that this is true. Now we've done one by Venn diagram and one by logical arguments.